All right, so welcome everyone to this new edition of the online Coworking Cinema. So the first speaker today is Carlos Arreche, and he'll talk about complex reflection groups as differential Galois groups.
Okay. Hello everyone. Thank you to the organizers for letting me talk here. This is joint work with the people you see here, Avery Bainbridge, Ben Overt, and Alavi Ula. We still haven't quite finished preparing the manuscript with these results. We started working on this as a group this past summer during an REU funded by the Sloan Foundation. And so all three of them are the undergraduate participants in a project that I supervise. And some of the initial ideas behind this project started when I first learned about reflection groups, working with a colleague of mine at UT Dallas, Nathan Williams, back in 2020. And back then, because of some stories that I hope to convey to you today, it seemed to me like you should be able to do something nice with differential equations, connecting my very old research interests with that very recent one. And well, I kept doing things wrong, and it took all these years for me to write down something that made sense. So I'm really excited to be able to share this with you today. So let me start with some background on these reflection groups. So first of all, a reflection is roughly what you want to think of a reflection as being. Normally, if you're in a real dimensional space, a reflection is a linear transformation that takes an n-1 dimensional subspace and treats it as some kind of mirror and reflects about it. Now we're going to be talking about complex reflections. The definition is a little bit different visually, but algebraically it's still the same. So a reflection is any linear transformation that has every eigenvalue equal to 1 except for a single different one. That's a root of unity. Reflections have to have finite order, by the way. So shearing transformations, something like the 2x2 matrix 1, 1, 0, 1, that's not allowed, even though it still fixes a one-dimensional subspace. Okay. And then a complex reflection group is a finite group of matrices that's generated by reflections. So this definition showed up back in the 1950s. The notion of complex reflection group was introduced by Shepard, and then they were completely classified. Think, if you like, of the classification of the Val groups of semi-simple Lie algebras. Different classification, but morally similar, by Shepard together with Todd, also in the 1950s. So initially, this notion was isolated because of what happens in the real case. If you look at matrices satisfying the same definitions as before, but replacing the complex numbers with the reals, you get what are called real reflection groups, and those really do behave like groups of transformations that are generated by reflecting about high-dimensional mirrors. As it turns out, real reflection groups coincide with the finite Coxeter groups. Those are finite groups that have a presentation of this particular form. Okay. Now here, my sentence says that one obtains precisely. This is imprecise. And the subtle difference is actually important for working in this business with reflection groups. So reflection groups, both real and complex, are actual groups of matrices. Okay. So groups of linear transformations rather than abstract groups. See, the definition of a Coxeter group is for a group that admits a presentation of a certain form. What is true is that every finite Coxeter group has faithful representation in which the image in matrices is a real reflection group, and every real reflection group admits a Coxeter representation. Okay, abstract versus actual groups does lead occasionally to some confusion when working with these things. Now, Coxeter groups, in turn, are a generalization of the Val groups of semi-simple Lie algebras with all the applications that you know. And finite Coxeter groups are almost all of them Val groups, except for 2 exceptions and 1 infinite family of exceptions that are quite well understood. Besides the analogy with the Val groups that have all these applications, complex reflection groups also have applications to a bunch of different areas. I don't want to trick you into thinking that I understand all of these applications myself. I borrowed this list from a fantastic book on reflection groups by Lehrer and Taylor called Unitary Reflection Groups. But they're really important, and they have a really beautiful invariant theory, as I'll explain next. So now for a finite group of matrices, or actually for right now, what I'm about to say applies for just any group of matrices. You can consider the the matrices in the group acting on the variables that go into an invariable polynomial, and then the invariant polynomials are the one that remain the same even after doing all those linear substitutions coming from your group. Okay. The collection of invariant polynomials form a ring called the ring or the algebra of G invariants. Now, the complex reflection groups are characterized amongst all finite groups of matrices as having the nicest possible invariant theory in the following sense. So give me any finite group of matrices, it'll happen to be generated by reflections precisely when its algebra of invariants looks like a polynomial ring again, but generated by some special homogeneous invariant polynomials that are algebraically independent. Okay. So having the nicest possible ring of invariants that you could hope for is equivalent to being one of these groups. Now, in my title, I promise to talk about reflection groups as differential Galois groups. I thought it might be useful and amusing to see reflection groups also being discussed as other kinds of Galois groups. The things that are going to happen in this slide coming up, I won't really use in too much of a serious way later. So I'll try to go over it a little bit fast, but just to give you an idea of all the different things that people do with these groups. So just to set up some notation, ref G refers to the set of all the reflections in G, right? Remember, these are the matrices that fix precisely a codimension 1 subspace. And for each reflection, you single out the subspace, the codimension 1 subspace that it fixes. Okay. And then you take the script H of G, it's a collection of all the hyperplanes that are fixed by all the reflections in G. So this is called a hyperplane arrangement. It's a particular case of a kind of structure that's studied a lot in combinatorics and by some people in algebraic geometry. Why it's relevant for us for reflection groups is that so you can consider the vector space that your group is acting on just a complex manifold with a G action, right? A really nice simple example of such a thing, and then consider the map that sends every point in X to its orbit under G. Okay? Y here stands for just that space of orbits. I'm calling the space, cheating a little bit, right? Not worried for the moment about its analytic structure or anything like that. But now what happens for reflection groups is that you can remove from X the union of all these reflecting hyperplanes, and then similarly remove from Y everyone in Y that came from one of these hyperplanes. Then when you restrict that orbit map to these open complements, you'll actually get a finite covering map from the open complement in X to the open complement in Y. And now you see you've removed from X the union of a bunch of linear subspaces, so that's still going to be a nice complex manifold, and therefore so is Y. And it's group of deck transformations. Okay, here's the definition. These things, you either come across this before now or not, but it's a well-studied kind of object, and it can be thought of as the Galois group of X over Y in a certain sense, but now within topology. Okay. Let me now briefly mention here that in fact this kind of picture has been studied a lot, because this finite covering map from the open complement in X to that in Y induces a short exact sequence of groups, fundamental group of X going to the fundamental group on Y with quotient G. And the fundamental groups of X and Y, suitably interpreted, are what are called the pure break group and the break group, respectively, of type G. And these generalize the classical Artin break groups that correspond just to the case of the symmetry group, considered as a reflection group. So it's a cool thing studied by a lot of people. Now going a little bit closer to the things that I really want to focus on. Complex reflection groups can also be considered as finite Galois groups of a certain field extension in the following way. So consider again the ring of polynomials in the variables that G is acting on, and then SG denotes the ring of G invariant polynomials. So I've already chosen some particular set of so-called fundamental invariants. It's important to note, I'll come back to this later, that the choice of homogeneous algebraically independent generators for the ring of invariants, that choice is not unique. But any choice that you make is, in a certain sense, about as good as any other, in a certain sense that I don't agree with today, as we'll see at the end of the talk. Okay, but let's fix a choice for the moment so we can continue this conversation. And the action of G on the ring of polynomials, just to be clear about things, to make it into a left action, you have to do this G inverse thing inside. This didn't come up when I was defining what it meant for polynomials to be invariant for the whole group, but now it's important to write down what the action really is. So here you have the field of rational functions now in the X's inherits an action of the group G from the one that you had on polynomials. And then you can similarly consider the field of fractions of the ring of invariants, which the latter ring talks like a ring of polynomials. So it also looks like a ring of rational function, a field of rational functions in some variables y1 through yn. And now you have a finite group acting on a field, and Artin's theorem tells you that that field extension is a Galois extension with the Galois group exactly the group that you started with. Okay. So this is all from theory. Let me mention that all those nice theorems characterizing reflection groups are actually proved this particular direction by Chevalier, precisely by pushing this Galois interpretation of a reflection group a little bit further than I've done here, just scratching the surface. And something that you would like to be able to do once you have a finite group being a Galois group is to say, well, when I first heard about Galois theory, my professor told me that it was a way to study polynomial equations. So where's the polynomial, right? I should be able to write down my big field L as a splitting field of some polynomial with coefficients in the smaller field K. So wanting to do this, not just in this particular instance, but for any one finite group that you're holding in your hand, is what's called the constructive inverse Galois problem, just for that little G. Here's this G exhibited explicitly as a Galois group, the Galois group of some polynomial. Okay? In a particular situation, it would be enough, if you like, to be able to find the minimal polynomial of each one of the variables x, because then from that you'll be able to create the polynomial that you want. Okay? And this seems like it shouldn't be too difficult. And I aim to convince you in two concrete examples that sometimes it's extremely easy, and sometimes it looks to me like it can be quite difficult. From theory, there's no problem, but in practice, you might run into some issues. Do we have any questions or concerns so far? Okay. So here's that first concrete example, the familiar example of the dihedral group of order 8. This is the symmetries of the square, and you interpret it as matrices in this particular way. This is not the only way to think of D8 as matrices. This is in fact the real reflection representation of the dihedral group. The way that the two generators act on polynomials is written down explicitly here, just to make things a bit more concrete. The first reflection negates the y-axis, so it's the reflection about the horizontal axis of symmetry, and the second reflection exchanges the two variables, so it's the reflection about the diagonal axis of symmetry of the square. In this case, one particular choice of invariant polynomials that generate the whole ring of invariants are this particular y1, x1 squared plus x2 squared, because this is the distance function and the reflections shouldn't change that. Okay, this is a feature of real reflection groups, that they always end up having the usual Euclidean distance function as their first invariant. For complex ones, this is no longer true, but we'll get there. The second invariant, I've chosen it here for reasons to be the product of x1 squared and x2 squared, and it's not the only one now. If you'll allow me to say that these two things definitely are invariants, then I could have replaced this y2 with the sum of the fourth powers of the x1 and the x2, and that would have also served as a different version of y2 for all the purposes that you want from theory. So in this case, there aren't any real issues with trying to find a polynomial whose Galois group is D8. Here it is. As it happens, well, there's some small details to check, so I'll ask you to just trust me that this polynomial works. You see that it has the coordinate functions x's as roots. And you can even, in this particular example, actually solve for the x's in terms of the invariance. From a modern perspective, there's nothing too interesting happening here, but for other reflection groups that showed up as early as the 1800s and some even earlier than that, being able to solve for the x's in terms of the y's showed up as a kind of important problem. People were interested in specifying this y1 and y2. They parameterize the orbits of G, right? So the y1 and y2, if you know what they are, you in a sense morally, you know you've chosen an orbit in X space for the action of your group. It's like okay, great. Which one? And if you can solve for the x's in terms of y's, this actually allows you to find which orbit you've specified by choosing particular values for y's. So in this case, this group has order 8. It's extremely small, and we got lucky where I don't need to with some nice new ideas to handle this group, because we can already exhibit it as a finite Galois group, and one might argue that that's better than doing anything differential here. Okay. So that's the sense in which we got lucky with this group. Now here's an unlucky one. This is a group of icosahedral type. Don't want to get too much into this taxonomy, but this is one of several different groups in GL2 that when you look at their projective image in PGL2, they coincide with a group of symmetries of the icosahedron. The presentation that I have here, if you're familiar with stories having to do with these groups, is not the one given by Klein. I like that one better, but I didn't have enough time to prepare this slide with Klein's choices. So I apologize for that if you care about this and you agree with me that this isn't the best choice to make here. But anyway, here's a group. It's generated by these three matrices. One can check that they are complex reflections in the sense defined in the first slide, and that the group that they generate is finite. None of this is obvious, but it's true. Okay. Here, you have a few different roots of unity, and then the golden ratio shows up as well in defining this group. So the algebra of invariance for this group, I'm in rank 2, so I expect to see 2 algebraically independent homogeneous polynomials, and they are here. Okay. They both happen to have degree 60, and Well, I guess it's a matter of taste, but these two polynomials are disasters. You know, this to me looks like space debris. Something blew up and people didn't pick up it for themselves. And so for this polynomial, I submit to you that you know, in theory, sure, you could find a polynomial with coefficients in the y's, whose splitting field is the field of x's. And if you want to do that, I wish you luck, but I don't want to be a part of that effort because it seems like it's going to be a mess. I'm claiming here that no one would be able to find a polynomial of degree smaller than 10 that does this. The reason for that is that 10 factorial is the first factorial that's divisible by 3600. And for G to be the splitting field of a polynomial, you end up interpreting G as a group of permutations of a set of n elements, which has n factorial as its size, and to be a subgroup, it has to divide that n factorial. Okay, so it's clearly impossible for such a polynomial to have degree smaller than 10. Look, 10 isn't like too big, right? This isn't scary. Now I've convinced myself that you probably can find a polynomial like this of degrees smaller than 30, which is now starting to sound a bit more scary. But just because I convinced myself doesn't mean that I can convince you. So I'm not going to try. I'm just telling you what I believe. If you want to know a little bit more, I can say more about why I think this later. But the point is that you know, there's some work to do, and it doesn't look like it's going to be easy. In this case, also, we definitely cannot rewrite the x's in terms of y's in a reasonable way using radicals because of the well-known story about solvable Galois groups corresponding to solvability by radicals. And this group happens to not be solvable because it, you know, contains has the alternating group in 5 letters as a quotient. Okay, so those are my 2 concrete examples. Stop me if you have complaints or questions, and if not, I'll go on. By the way, to the organizers, good question. When should I stop?
Oh, I think we said it's a 40-minute talk. So yeah, we started a little late. So yeah,
so another 15 minutes or so.
Yeah, that sounds good.
Okay. Thanks,
Carlos. I had a quick comment.
Oh, sure.
Because your reflection groups are generated by elements of order 2, when you start looking at invariance, it doesn't really matter that the left action on the polynomial ring is through inverses. But I would just comment that in some contexts where you have a left action on the space on the polynomial ring, you like to make that a right action, and that was the convention of your mathematical grandfather. So with that, we can go back to the talking.
No, thank you for the comment, and let me add that it is indeed true that for real reflection groups, the reflections have order 2, but for the complex reflection groups, they don't. And for them, it really does matter to write things down in the way that I said. For example, here, this group has reflections of order 2, but also of order 3 and order 5. Just because I'm allowing myself to use the word reflection in this complex sense where just finite order having an eigenvalue being an interesting root of unity, not just -1. So these groups are strange, but they're also beautiful. Okay, so I can't remember what the next slide is. So let's find out together, shall we? Right. Now I start talking about interpreting these groups as differential Galois groups. So this is a well-known story to the experts, but let's do a quick recap. And again, stop me if there's something I'm saying that's not completely clear. So first of all, because my field L, rational functions in X's, is a separable algebraic extension of K, then the standard coordinate derivations from K extend uniquely two derivations on L. Not only that, but they used to commute down in K. They'll keep on commuting up in L, because in any case, the commutator of two derivations is always by rights a derivation again. That derivation is 0 on K, so it extends uniquely to the 0 derivation on L. Okay. So these derivatives with respect to the y's act on L somehow. How exactly they act on L is an issue that we'll come back to. But by theory, there's a unique. It makes sense to think of L as a differential field extension of K for a standard differential structure as a field of rational functions. Not only that, but it's also well known within Picard-Bessel theory that anytime I have a finite Galois extension of fields that happen to be differential fields, then it's also a Picard-Bessel extension, right? A quick reminder, what does that mean, especially in this context? So now my delta, is sort of an ordinary differential field extension, but you have several partial derivations. I need to be able to find one matrix for each derivation such that the matrices are compatible with one another, satisfying this integrability condition. This is the same as asking for the derivations to keep on commuting in these Picard-Bessel fields. And then also the field L has to have a fundamental solution matrix for the system of equations defined by the AI matrices. Okay. So what I mean by saying that L is a Picard-Bessel extension of K is exactly these two items. I can find matrices A together with some matrix U with entries in L that do this. And here I'm being a little bit coy because I don't want to tell you the future yet. This capital N in here, I'm not telling what it is. It could be anything. Okay? If there's an N allowing me to write down these two items, then I've exhibited L as a Picard-Bessel extension. And now, for any collection of matrices A that you can find that do all of these things, then L considered as a differential Galois extension of the field K is going to have a differential Galois group, and that's going to be identified with G, but not necessarily in the obvious way that you would like, depending on how you pick these matrices A. The way in which you take Picard-Bessel group and think of it as a group of matrices is after having chosen one fundamental solution, then you interpret automorphisms of L over K as matrices according to this particular recipe. Okay, so you'll have one group of matrices that's abstractly isomorphic as a group to G, which was again a concrete group of matrices, but maybe not directly in the same way that you had the G originally. Okay. We'll end up doing better and actually finding G as a differential Galois group exactly in the way that it was given at the beginning. But so far, what theory tells you is that you could find some group of matrices that's isomorphic as a group to your group G. And now, okay, so still keeping the same notation, right? L is the field of rational functions in the x's that G is acting on. K rational functions in the y's, some choice of invariance. And what I would like to do is to actually construct or compute explicitly some system of differential equations having G as my the original G I was given as the differential Galois group for that system. Okay. So there are some problems that you run into here in trying to do things explicitly rather than just saying, well, theory says these things exist. And the first one is how exactly can you right? So both L and K are very concrete fields of rational functions, and the deltas that I have acting on K are partial derivatives with respect to coordinates. I have no questions about the deltas acting on K. And now give me some rational function in L and go ahead and differentiate it, right? What should you get is a mystery, right? Okay, but this situation has shown up a lot. It's kind of well understood. What you see in books, in the proof that any separable algebraic extension and it's a unique extension of any derivation from the base field, is this. You take any one element in this separable extension, you find some separable polynomial that it satisfies, whether the minimal polynomial or a different one doesn't matter. And then it turns out that this formula tells you exactly how to differentiate any such element within L. But here in the context that we're discussing today, my problem is that I don't know how to find polynomials for elements of L. So if I was able to find how to differentiate elements of L in this way, then I would have already won. Okay. So we're not allowed to do this, and that's a problem. We need to find a different way to explicitly compute the derivations on K, how they act on L. Next is that because you have several derivations, you might have some ways and tricks to construct linear differential equations for each one of them separately. But some ways of doing this, the first ones that I thought of, end up not working because I end up with one differential equation for each delta I, but they are not compatible with one another. Okay, so these choices have to be done for, if you like, for all the deltas at once. Okay. And that's another issue that we have to get past. And then lastly, how to say, in the middle of a talk, like these are obstacles, and now you can expect that next I'll say, and we overcame them all, success. We're still working on this last thing. Okay, but how large do I need my system to be, right? Already you have a finite k-dimensional vector space with a differential structure, and that's L itself. But the dimension of L as a k-vector space is well known to be the same as the size of G. In our example that I called small-ish, G had order 3600. Some of the G's that we care about have orders in the hundreds of thousands or hundreds of millions. Okay, this is not reasonable. Even if you can compute a matrix like that, I can't read it, so it's no good to me. How small can you get just the rank of these matrices? And then secondly, the entries in the matrices. How complicated of irrational functions are you going to get there? Okay, for the one complicated group I showed you, G19, we had invariants that were annoying to write down, and you kind of saw them but didn't read them, right? If that's what my matrices look like, then once again, what's the point of having them if I can't read them? So these are problems that I care about, but maybe they're minor compared to the first two more serious obstacles. So before I tell you, how to deal with these things in general, let me just show you the results in the examples. If I run out of time, then I really wanted to see at least this. In the case of the dihedral group, these are the matrices that we computed with a recipe that I haven't told you yet. So this is a little bit annoying to me, to be honest with you, because these matrices are not terrible, but the group itself only had 8 elements. So like no one has any serious questions about the 8, and actually we already have a polynomial exhibiting D8 as a Galois group. If you have that, then somehow this differential story seems like overkill. Okay, like what's the point of finding these differential equations if they are not better? This is a feature, not a bug, of a lot of the groups in the Shepard-Todd classification, the ones belonging to these infinite families that I mentioned really, really quickly at the beginning. Okay, I will say that even for those groups, we have a recipe for computing these differential equations, and why I don't want to insist on this too much, but why that might be interesting anyway is that reflection groups once again are given to you originally as matrix groups. What you do when you interpret them as Galois groups of a polynomial equation is that now they become permutation groups on a set of roots. Okay, and it seems to me like you're somehow forgetting something important about the group, in that now you only know it kind of as an abstract group, not anymore as a concrete group of matrices. Okay, this kind of subtle difference between reflection groups and abstract groups. And when you have the differential equations, you actually see G as a Galois group exactly the way it was written down at the beginning of your story. Okay, so I find this nice anyway, even though I wouldn't argue too much with someone who tells me that there isn't as much of a point for these groups. Now, I really want to get to the G19 because you remember how terrible it was. Maybe you don't remember. So let me show you again. These were the invariants of G19. Okay, disaster, space debris. Hate staring at this, and yet so they're so bad that I honestly don't know how to compute this polynomial except to tell a computer the right things and just wait a few hours or a few days. I have no idea what would happen. And the differential equations though are these, and this is not a matter of taste anymore. You have to agree with me that these are extremely simple, and this is surprising to me. That's something that I can't compute from the finite Galois theory side, which somehow like a simpler theory, or at least earlier, should become jokes when seen differentially. Okay, so this is very heartening for me to see, and kind of for motivation to continue this project and get a few of the remaining groups that we don't have yet. Okay, so let me tell you a few words about the recipe. You'll remember my first obstacle was that I didn't know how to let the y derivatives act on the field L, and that turns out to be easy to compute. I just didn't see how for years. So the y's are actually polynomials in the x's, so you can differentiate them with respect to the x's and write down this Jacobian matrix. And by reasons that are well known, but here are in very tiny print some details that I won't give you time to look at. When you compute the inverse of this matrix, you'll get some rational functions in x, and from them you can read off exactly what the delta should be doing to the rational functions in x. Okay, so this inverse of the Jacobian matrix will tell you how to differentiate each x, and then now you can differentiate any rational function in the x's using the derivative rules. Okay, so the first problem isn't much of a problem at all. You just have to compute this matrix and then invert it. And now with having access to these derivatives, then here's a recipe for finding the A matrices that I want, right? These are the coefficient matrices in my differential equations. You take that same Jacobian that you had to use earlier to compute the action of the deltas on L, and then you construct the A's in this simple way. Basically, it turns out that the Jacobian is going to be a fundamental solution matrix for the differential equations that we don't have yet. I don't understand why this works. The Jacobian is a very classical, well-understood object, and reflection groups are also extremely well studied. This is a very simple construction, and I'm just surprised that this was the thing that I kept not finding for all these years. If anyone has some thoughts on why it is that these A's do what I want, I would love to hear them. To me, it's a bit of a happy accident and mystery. Okay, and now so these A's really do what we want in that first they have entries in the field K of invariance, even though this J has entries, rational functions, well, polynomials in X. J inverse now has rational in X entries. When you differentiate the J, you introduce ridiculous looking expressions depending on how bad the invariants were, and then at the end of the day, this X mess ends up being rewritable in terms of the Y's. The integrability condition ends up coming for free, but it has to be checked. And then finally, we can also check that L really is generated as a field extension of K by the entries of the Jacobian matrix. This is obvious in the case of real reflection groups because you have an invariant of degree 2. So when you differentiate it one time, you end up finding all the X's already as entries of the Jacobian. But for other reflection groups, it's not obvious to me. And most of this is proved by all computations or using the Galois correspondence. Okay. I only have a few minutes left, so I just want to finish. Or actually, I have maybe 0 minutes left, but not negative yet.
Don't worry, it's fine. You can have a few more minutes.
Okay. It should be just 1.5 or so. Let me finish on these 2 comments first. that the recipe that we have is all based on doing things with the Jacobian matrix. I write down the Jacobian matrix the moment I have some choice of fundamental invariance for my reflection group. There are different choices that one can make. And we have seen in many cases that making the wrong choice, whatever that means, gives you extremely ugly matrices that you cannot print in a page. And then making the right choice gives you lovely matrices like the one that I showed you in the case of the interesting group G19. Okay. So part of what's holding us back in a few of the examples that we don't have yet is computing or finding not just any invariants. Computers can do this, but invariants that somehow are geometrically meaningful, because those are the ones that are going to give us nice answers that we can stare at and maybe learn something new about these groups. Okay. So this is an interesting kind of phenomenon. And then next, Michael Singer pointed out to me, and then later Jacob Vey, pointed out to me the same thing, that this is not the first time that someone has produced differential equations realizing reflection groups as differential Galois groups. There's this work, well known, except to me, amazing work by Boykers and Heckman, where they find conditions on the parameters of a generalization of the classical hypergeometric equation that guarantee that its Galois group will be any reflection group that you want. I think they have tables at the end, and I still have done the work of carefully checking that every single reflection group does appear. But I'm told that is indeed what they have. Okay, so I think it would be really interesting to find what connections there might be with their differential equations and ours. But right now we don't know. Okay. And with that, I think that's all I have. Thank you so much.
All right, thank you so much, Carlos, for this very nice talk. Do we have any more questions or comments from the audience?
Oh, please. I have a question. So, have you done any research into telling which approach would be better, like before you get into it?
In what sense? Which approach to do which part?
Yeah, so you had like two approaches to find these groups, and you had lots of great examples where one approach was like awful or even impossible. Do you have any like sort of a priori checks? Have you looked into that at all? For which one?
Yeah. So this whole thing started because already classically reflection groups are known to be like a classical Galois group of a finite algebraic field extension, right? And then I thought like, well, that sounds great. Where's the polynomial? And I couldn't find it anywhere. Couldn't find it because people didn't write it down. They didn't write it down, I think, because it's really hard.
Yeah.
This doesn't happen for all the groups. So in fact, let me go back. I kind of mentioned something obliquely about this. In the case of the dihedral group 4/8, we have differential equations. We can find them, and they're not terrible, but not great. The polynomial itself is beautiful, though. You know, its coefficients are negative y1 and y2, and you can immediately write down. Now I know a polynomial like this for infinitely many of the groups showing up in the classification of irreducible groups. Okay, so for all of them, they're somehow all constructed from starting with a symmetric group and then putting a funny twist on it. Okay, and then the elementary symmetric functions end up giving you polynomials for them. So for those, our contribution is a lot less clear, and I wouldn't go out and study them differentially because the polynomial approach seems better. But for all the other groups, the exceptional primitive ones, I don't know of polynomial equations, and we actually have all of them. Let me see if I can quickly show you a thing. So we found all the rank 2 differential equations. Can people see my screen now?
Yeah.
And so these are all of those exceptional groups that have rank 2. And you know, of course, I'm not asking you to read all these tiny matrices, but just to look at how they fit in a page. Okay, and that's actually amazing. For the groups that we have left, they are ridiculously huge, and I don't expect the polynomial approach to work at all. And for those, we're still looking for differential equations. I hope I answered the question. Sorry, that took a while.
No, definitely. Thank you.
Thanks.
All right. Any more questions, comments? Maybe one thing I was wondering is, so your construction of the integrable system, it only depends on the generators of the invariant ring. And
correct.
Yeah, so how about the construction of the polynomial P? I think is there a construction of the polynomial P which is like this, so that it only depends on the generators of the invariant ring? I think you didn't really go into somehow how, like, what is the general way to construct the B?
Yeah. So if I had to construct P to save my life, I would run really fast. But like, I think you have to do some elimination theory, right, to eventually get these relations amongst that. Also, so you're given ahead of time by writing down the invariants, some polynomial equations that the x's satisfy that make them equal to y's. And so using those, you could eventually cook up the minimal polynomial for each one of the xi's, and then multiply them all together, and that P is going to work. Is it the best possible P? Who knows, right? I doubt it. That's what I would do. But in general, I don't know that there's any reason, at least from theory, to like have a preferred approach to construct polynomials realizing a field that you already have as as a splitting field. For reflection groups, maybe there are some nice reasons to do it. In fact, I also mentioned somewhere, kind of really quickly, that that I expected the degree of some polynomial to be at least 30 for the G19 group. So what I would try to do for reflection groups is hope that a few vectors in the in the span of the axis have very small orbits for G. Okay, so the ones that are sorted ahead of time are the things that lie in the reflecting hyperplanes, and this particular group, there's a collection of hyperplanes that form an orbit of size 30. Okay, so these 30 vectors together should span a two-dimensional vector space, right? And I know I can find a polynomial of degree 30 realized in this group. I expect that that's somehow optimal and that's possible. But the short answer to your question is that I don't know that this question has been studied to the point where there's an easy answer for it.
Okay. All right. If there's no more questions, let's thank Carlos again.
Yeah. Thank you.
And so I'm looking forward to seeing everyone again next week. And if I remember correctly, is Thomas Dreyfus speaking.